Hello, this is Professor Dan Kernler again, and today we're working on section 17.4, which is about Green's theorem. Um, Naturally, we had to change the background in the notes to green. We'll have to do a green marker for this section just for comedic value. But I'm going to do a couple things here. I'm going to introduce the idea, and then I'm going to actually leave the derivation to another video, which I will link above and put in the description, which is a better visual, a better production value for explaining the reasoning behind this particular theorem. So for Green's theorem, first of all, let's recall back to section 17.2, we had this definition of the circulation. And the circulation of a field, was simply a measure of how much of the vector field points in the direction of a curve. And that simply was the line integral. The line integral of the vector field, the dot product with dr, that gives you the circulation. And so let's jump back over to Green's theorem now. Just to recall here, so the circulation is the line integral over the curve of the dot product between the vector field and the tangent vector ds, or we can write that as the line integral of the field dot product with dr, which we know was r prime of t dt. So if the circulation is not zero, one of the things we're going to use here in Green's theorem is this idea of, okay, we're looking at how much of the field is pointing in the direction of the curve, of the motion that you're going around this curve. If the circulation isn't zero, there has to be something inside the curve causing that circulation. So if we look in 2 dimensions, we're going to focus on a curve that is oriented in the clockwise or counterclockwise direction. And so if that circulation that we get of the curve, we're trying to see how much of the field is in the direction of our curve, there must be something inside, like a little paddle wheel, causing that circulation inside. And so if you want to right now, you can pause this video and go watch the derivation of the Green's theorem video that I mentioned earlier and that I will link up here. We are going to jump to that now and just write and talk about the Green's theorem, what it is, and then do a couple of examples. So we're going to learn 2 forms for Green's theorem. One is the circulation form, which we have our line integral here, which gives us the circulation. We have the differential form of that. You can look back and see that in your notes. And here's what Green's theorem says. What we can do instead of finding the line integral to get the circulation is we can actually do a double integral of this thing, whatever this is, this partial derivative of g with respect to x, partial derivative of f with respect to y, over the area. So instead of doing a line integral over the curve, we can instead do a double integral inside. I'm going to jump down here and give a definition, and then we'll jump back up. So this thing that's inside is called the 2-dimensional curl. And what it is the partial derivative of g with respect to x minus the partial derivative of f with respect to y. If that curl is always 0, then there's no rotation in that field or in that region, so we say it's an irrotational. The vector field is irrotational on that region. So let's jump up here and talk about what is this actually measuring? What are these partial derivatives? So what I have here is the red arrows are meant to illustrate portions of a vector field, and we're looking at a specific point here. And so what we're looking at is we have a vector field that is some function f of xy, and then some function g of xy. Let's see here. Okay, get my notation right. And so if we have that vector, here's our vector there, there's some x component to it. Let me be a little more precise. There's some x component to it, that's the f, and then there's some y component to that's the g. And you look at those together, that gives you your field f. So let's look at what's happening here in this particular kind of demonstration. If we look at just the y components, as x increases, you can see that these y components of the vector appear to be increasing. G is the y component. G is the y component. So we're looking at, look at x is changing, x is increasing to the right. So as x increases to the right, we'll just say as x increases, and the right is implied there. G, let's write it in there. The y component of our field, which is G, increases in length. So that's a rate of change, right? That's describing as x increases, y increases. So what's happening here, that means that the partial derivative of g with respect to x is a positive number. Okay, let's look at the x components, all right? And we'll look at the x components as y increases. So these are the x components. You can see they're intentionally designed to get smaller. So we can see here that the x component of our vector field f, which is the function f with their lowercase f, is decreasing as y increases. Well, that implies then that the partial derivative of f with respect to y is a negative number. Okay? So if we take those two facts together on this particular example, we don't really have a field, we don't even have the entire field, we're just looking at two little strips. But if we look at those together, that means the partial derivative of g with respect to x minus the partial derivative of f with respect to y is some positive number. Because the partial derivative of g with respect to x is already positive, and then we're subtracting a negative number, so we definitely get a positive number. Okay, well then what that means is the double integral over that region of this partial derivative of g with respect to x minus partial derivative of g of f, with respect to y, dA must be a positive number. So the reason why we're mentioning this is that means that this particular region that we were looking at would have some rotation to it. There'd be some rotation, general rotation in the counterclockwise direction. There'd be some rotation due to the field. Okay? So what that means is that there is a positive curl, and what the theorem, Green's theorem, says above is that the circulation on the curve, how much of the field is in the direction of whatever curve we have. So say we drew some curve around this. The circulation on that curve is equal to the rotation inside, the curl inside. And that's what Green's theorem is. The power of Green's theorem is it relates a line integral along an edge to what's happening inside the region. And that's the power, that's what Green's theorem is. One last fact on this side, and then we'll do an example. So what would happen if those two partial derivatives were equal? Well, think about that. If they were equal, well then the line integral, and this is actually over a closed curve, so I should be doing circles here. What that would mean is that would be the double integral over the region of the partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. If those were equal, then that's just 0. And so think about that. What does that mean if you have a line integral and a closed curve and you get 0? That isn't always the case. Hopefully you remember that means that the field is conservative. Do you remember? That sound familiar? If you get 0, also if these cross partials are equal, you get 0, that means it's conservative. So that's an interesting note there. Okay, let's move on and do a couple of examples here. First use of this one, we're going to use Green's theorem to compute this line integral along the closed path here. I have the path C. It's kind of like C1 and C2. C1, I believe, is supposed to be x squared. Looks like 1, 1, 2, 4. And then C2 looks to be 2x. C is the path defined, oh yeah, there we go, given by y equal x squared and y equal 2x in the counterclockwise orientation. Okay, so we have this orientation, and we're going to try to compute the line integral. So we have two options here. We could compute the line integral as a line integral, but that'd be fine. We just do the line integral over C1, and that's not closed, so that I wouldn't do the circle on that one for that line integral, and then I would add the line integral for C2. Right? That is certainly possible. What we are going to do instead is use Green's theorem. We're going to instead do the double integral over the region inside, and then we'll have the partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. Let me pull up a maple graph of this so you can kind of see what's happening. So here's a maple graph. What we have here is, I have these vectors, they all look like they're the same length. What I did is, this is kind of a common tool here, some of them end up looking like almost zero. So what I do instead is colorize them by their length. So red is going to be closest to 0, and then the further on, not the further on, but the further around the color wheel there you can think of, there's red, orange, yellow, green, blue, and then to magenta at the end. So those are getting longer. They're getting longer toward that end. And then what we're going to try to do is we're going to try to find the line integral to get the circulation, and instead by doing that we're going to integrate the curl inside. That's what we're going to do. We're going to see if there's any rotation to this. So we have our field. This is our F, and this is our G. So it's going to be the double integral over the region. Our G function, we have to find its derivative with respect to x. That will be 2x plus 2y. And then we're going to subtract the partial derivative of f with respect to y. So that's minus 2y dA. Well, that's nice. That's just the integral of 2x. And let's do dy dx. And now we're going to set up a double integral. You can think of your rectangle double integral. You're going from the bottom curve, x squared, to the top curve, 2x. And then x is going from 0 to 2. We are integrating y first. So 2xy from x squared to 2x. And we still have a dx there. It's the integral from 0 to 2 of 2x times 2x minus x squared. Nice little polynomial here, integral from 0 to 2 of 4x squared minus 2x cubed. And that will be 4/3 x cubed minus 1/2 x to the 4th from 0 to 2. And let's see, 4/3 times 8 minus 1/2 times 16. 32/3 minus 8. 8 would be 24/3, so we'd get 8/3. So what this means is this is greater than 0, so the circulation is positive. It's in the direction of the curve, so that means it's in that counterclockwise orientation. The circulation is positive. I will say the maple graph, it does not look obvious here. It kind of looks like it goes with it on the parabola, and then we're going kind of against it on the line. But it has to do with the angle that they're at. There's something there that's giving it more with the direction that it's moving here. So something about that field. That one, I think the maple actually is a little, it doesn't really reinforce what we got there as a result. It's not obvious. The next one, though, will be. Let's do another one. So here we're again going to find the line integral, and it's giving it to us in differential form. This is our f. This is our g from our field. And c is the path given along these half circles. And again, we're going to orient this in the counterclockwise direction. Okay? And so instead of integrating this in its differential form, we are instead going to do a double integral over the region of, let's see, we need the partial derivative of g with respect to x, and it'll just be 2x, minus the partial derivative of f with respect to y, that's 2y dA. And now we have to define our double integral, and you might be looking at this like, well, these look circular. Can we just use polar coordinates? Yeah, in fact, you should. That would be great. Let's see, we have, well, let's see, x is r cosine theta, and y is r sine theta. We're going to do r dr d theta. R is just going to go from the inner circle to the outer, so the radius is from 1 to 5, and theta is going to go from 0 just to pi, not all the way around this time. Let's pull out, we can pull out the 2. I guess, I don't know if that's invaluable. But then we're going to have an r squared, and then cosine theta, oops, sorry, still need the integral there. Integral from 1 to 5. Let me put the 2 with that, sorry. 2r squared, and then cosine theta minus sine theta, dr d theta. So I multiplied the r in, well, I kind of factored out the 2r and then multiplied by r. And I just thought it'd be valuable to separate the r's and thetas because we're going to integrate them separately. And so let's integrate r. That'll be 2/3 r cubed from 1 to 5, and then we still have this cosine theta minus sine theta d theta. And let's see here, 5 cubed is 125 minus 1, so it's 124. 124 times 2, so 248 thirds. And then we have cosine theta minus sine theta d theta. Okay, 248 thirds. The integral of cosine will be sine. Then plus cosine theta from 0 to pi. And let's see, sine of pi is 0, cosine of pi is -1, minus sine of 0 is 0, cosine of 0 is 1. Looks like we get -2 in there, so -496 thirds. So that's, wow, that's very negative, very negative. What that means then is that the circulation is the other direction. It's the other direction. And check this out. This one, if we go over to our maple, you can see very clearly that if we want to move counterclockwise around the edge, it's almost always in the opposite direction. All of these arrows are almost all of them are in the opposite direction, especially on the outer edge. We're definitely going to get a negative circulation there. Or if you think of it inside, the rotation is actually clockwise. So this is the two ideas. It's for the line integral. It's a negative circulation. And for the double integral over the region of the curl, that means a counterclockwise or clockwise rotation. That means it's rotating clockwise. Okay? So that is it for this video. In the next video, we'll talk about another form for Green's theorem. We've been looking at the circulation. How much of the vector field is in the direction. Instead, you can just integrate the curl inside. If you recall, we also had the flux, kind of how much was going outward. And again, we're going to be able to look at a line integral and compare that to what's happening inside of the region. So that is it for this video. We'll be back with another one right after this. So that is it for this first video in section 17.4 about Green's theorem.